All right, we are now ready to begin talking about Chapter 15 on acid-base equilibria. As always, remember that your book problems are going to be listed on slide 1 of this particular set of slides. All right, now moving on to slide 2, we're going to introduce this idea of common ion solutions. So up until now, we've only talked about what are called standard solutions. Okay? A standard solution, for example, is when we would add something like hydrofluoric acid to water and we'd make an aqueous solution of that. Okay? Since HF is a weak acid, it's going to partially dissociate and is going to establish an equilibrium, right? Where we had our HF, it partially dissociated into our H plus ion and our F minus ion, and it established this equilibrium between those two states. All right? Now, another type of solution is what's called a common ion solution. Now, these solutions are going to contain two compounds that contain a common ion between them. So, for example, let's add sodium fluoride to our HF solution that we started with. Okay, and what's going to happen? Well, the sodium fluoride is going to dissociate, and when it does that, it's going to add the F minus ion into that solution. Okay, because our sodium fluoride is a group 1 salt, and so it's going to end up splitting up into that completely, right? Because those are going to completely dissociate, okay? And we're going to put in a lot of F minus into that solution, okay? Once we've added a bunch of F minus, okay, then we know that the sodium fluoride and the HF are going to share that ion in solution, okay? Now, because of that, that means that our original equilibrium that we formed with the HF in our aqueous solution, it's going to shift, okay? Because what has happened is when we added our sodium fluoride, right, it put in a whole bunch more of that F minus in solution. So this team became stronger in our equilibrium, right? And so we are going to shift to the left because this team is stronger, okay? So shift to the left, right, or to our reactants, okay? Now, because of that, that means that our common ion solution is going to be less acidic, right? Because when we've increased our concentration of F minus, it shifted our equilibrium to the left, which meant that our concentration of H plus had to go down when we shifted to the left, okay? So our system is going to be less acidic in this common ion solution, right? Now, let's move on to our slide 3. Oh, goodness, lots to erase. Now, on slide 3, we're going to talk about our next type of solutions. So we've introduced our standard solutions, the common ion solutions, and our next one is going to be called a buffered solution. Okay? Now, a buffered solution is going to resist change in pH, okay? They resist change in pH even when a hydroxide ion or H plus ion is added to the solution, okay? Now, the way to make a buffered solution is with a common ion, okay, using 1, a weak acid and its conjugate base, Or a second option is with a weak base and its conjugate acid. Okay, so moving on to slide 4, let's see how this works. Okay. Right? So if we want to know how does a buffer work, let's say we have a weak acid and a conjugate base. Right? That's our first case here, right? And let's say that our weak acid is HF, and we have F minus, say for the case where we added our sodium fluoride, and then we did that in equilibrium, right? So once we've added our sodium fluoride to our solution of HF, it's established some sort of equilibrium, right? Well, once it's at equilibrium, if I add a little bit of H plus, okay, then what's going to happen? Okay, if I add a little bit of H plus, it's going to quickly react with the extra with the extra F minus, right? Right, remember this is the conjugate base of a weak acid. So if we've added any H plus, remember it wants to go back toward our HF, right? Remember we have our equilibrium HF and it favors being protonated, right? Because it's a weak acid, all right? So if we add any extra H plus, that means it quickly goes over to our HF side. Okay, so it didn't affect the pH at all, even though I added a little bit of H plus. Okay, so this doesn't really affect our pH, right? Now, what about if I now add a little OH? Right, we had a little bit of hydroxide. Well, if I add a little bit of hydroxide, it's going to react with our HF in solution. Right, and when it does that, it's going to pull off a little bit of our H plus, right, from this, okay? But when that happens, the equilibrium is going to push us back and pull more of our H out of solution. Okay, so that equilibrium pushes us back, right? So even though, right, you can sort of think of it, right, we still have our equilibrium here, right? If I've added our OH, okay, then that means that my OH is going to pull an H off of that, which means this is going to go down. But when that happens, I've still got plenty of F minus in solution. So it's just going to continue to push me back with our driving force being our equilibrium constant. Okay? So no matter whether or not I've added a little bit of acid or a little bit of base, right, my equilibrium is going to be reestablished. And when that happens, right, my pH isn't going to change. All right, so let's do an example. And again, while we're talking about this, this effect is the buffering effect, okay? And the reason we call that is because it buffers any changes, okay? It accounts for any changes that come about due to adding any sort of pH change, whether that be an H plus or an OH, right? Because again, if we've added any H plus, right, it's going to react with the extra F minus, okay? So it's taken out of solution. And if we added a little bit of OH minus, it reacts with the HF, but we have plenty of the F minus, so it just continues to reestablish the equilibrium, right? And our pH doesn't change a whole lot, okay? So on slide 5, right, I said I'd give you an example, so let's see how this works, right? So for buffer problems, you know how much you guys like steps. So here are the steps to solve a buffer problem, right? The first thing you're going to do is find your initial concentrations. Okay? The second thing that you're going to do is you're going to set up an ice table. Right? And the reason we need an ice table is because there's going to be some sort of equilibrium involving that common ion. Okay? Our third step is going to be to use information that's in the problem to solve for the equilibrium concentrations. All right, just like all that stuff that we've done a bunch. All right, and then our fourth step is going to be to solve for our pH or our pOH or whatever it's asking for. Okay, so for example, right, this is on slide 5. All right, here we have a buffered solution. Right, and I should say we have a buffered 1 liter of solution, and that solution contains 0.50 molar acetic acid. Okay, now acetic acid, that's going to be our weak acid, right? And 0.85 molar sodium acetate. All right, and that sodium acetate is going to contain our conjugate base of this weak acid. All right, the acetate ion is going to be our common ion in the system. Okay, and from this, let's calculate the pH of our resulting solution. Okay, and we also need to know that our Ka for acetic acid is 1.8 times 10 to the negative 5th. All right, so our first step is going to be to write our initial concentrations. All right, now our initial concentration of HA, right, that's our weak acid, is going to be 0.5 molar. All right, and our initial concentration of our ion, right, our conjugate base ion, is going to be 0.85 molar, right, because it's a 1-to-1 ratio for sodium acetate to our acetate ion, okay, which is going to be our A minus. All right, so those are our initial concentrations. Our second step is going to be to set up our ice table, all right, where we have HA, there's an equilibrium with H plus, and our acetate ion, ICE. Again, we should be pretty well versed in these tables by now. right? We then plug in our initial concentrations, right? Our initial concentration of HA is 0.50 molar. Our initial concentration of H plus is just 0, okay? Because we didn't have any of that information, and any of it that's been added has already been pushed, or any H plus that we had has already been pushed over by the addition of that acetate ion. Remember, our equilibrium is going to shift to the left, in this case, for our acetate ion, common ion equilibrium, okay? Then we have 0.85 molar for our acetate ion, all right? And again, this is our initial, okay? Then we have 1 times negative x, 1 times positive x, right? Because it's a product. And we have our stoichiometric coefficient again, positive x, all right? We add these up and we get 0.5 minus x, x, and 0.85 plus x. All right, now, this is important. Step 3, right, that's where we use information from our problem statement to solve the equilibrium, or solve for our equilibrium concentrations, right, in this row. The first thing that we're going to want to do, all right, and this is different for the buffers, okay? In a buffer solution, okay, our concentrations don't really change much. And so what we're going to do is we're going to set our weak acid and conjugate base, or our weak base conjugate acid, depending on what type of problem we're working. Okay, we're going to set our weak acid conjugate base change, right? That's this line, right? We're going to set that change equal to 0. Okay, so what do I mean by that? Well, what I mean is that if we have an equilibrium problem and it's buffered, okay, then that means that our equilibrium change, these x's, right, they go away. All right? And that's because our concentration of HA and our concentration of A minus, they don't really change much because of the shift that happens due to the equilibrium constant. Okay? Now, once we have that, that's step A. Step B is just to set up our KEQ expression, right, our equilibrium constant expression. Well, we just plug in our equilibrium values, right? So we have X. Well, let me do this first. It's our concentration of H plus to the first, our concentration of A minus to the first, all over our concentration of HA to the first, again, all at equilibrium. That makes this expression equal to 0.85 molar to the first times X to the first, right? Our products, and then over our reactants, which is 0.5. Okay, we know what our Ka is because this is an acid dissociation problem. Okay, so that means that we have 1.8 times 10 to the negative fifth, right? And we know that that's equal to 0.85x over 0.5. We solve this for x, and that is equal to 1.056 times 10 to the negative fifth, okay? Now, since we made this assumption, okay, we'll have to do our 5% rule, okay? It ends up being 0.002%, which is really less than 5%, okay? Now, our X is our equilibrium concentration of H plus, right? Which means that our last step, which is to solve for our pH, right? So step C in this would be to solve for HEQ. Step 4 would be to solve for our pH. We know that pH is equal to the negative log base 10 of our concentration H plus at equilibrium. All right, so we would just plug in that value and we would end up getting a pH of 4.975. 5. All right? Now, I think that this will be a good place to stop, and then what we'll do is we can go through an example of adding base to an acidic buffer in our next video.